In this video, we'll be using all the limit rules we've learned so far to find limits. We're going to start this video with an important theorem. It states if f is a polynomial or a rational function and a is in the domain of f, then the limit as x approaches a of f of x is equal to f of a. Basically, what this means is as long as the x value you're approaching is in the domain, all you need to do is substitute that value in for x and clean it up, and you'll have your limit. This also extends to our trigonometric functions as well. So let's find the limit as x approaches 6 of x minus 5 over x squared plus 4x minus 1. Now we need to make sure that 6 is in the domain, and since this is a rational function, we know we have to be concerned with where the denominator is equal to 0. Usually what I do is I just take the 6 and plug it into the denominator and see if I get 0. If I do, well then I'll address that problem. If I don't, then I'll just clean it up. So let's plug 6 in. I'm going to plug into both the numerator and the denominator. We get 1, and in the denominator, that's 36 plus 24 minus 1. Certainly not 0 in the denominator, so we'll just clean it up. We end up with a limit of 1 over 59. Next, we want to find the limit as x approaches 3 of x squared minus 9 over x minus 3. Well, I can see at first glance if I plug 3 into my denominator, I'm going to get a 0 down there, and that's an issue. So we need to address this. Although this function may be undefined at exactly 3, remember with a limit, we're not necessarily concerned with what's happening exactly at 3, but just as we get really, really close to 3. We want to try to simplify this so that we don't end up with a 0 in the denominator. Let's see if we can simplify this rational expression. We simplify rational expressions by canceling common factors. Difference of 2 squares in the numerator. X minus 3 in the denominator, those are going to cancel. We're left with the limit as x approaches 3 of x plus 3, and now there's no problem plugging in. 3 plus 3, this limit is equal to 6. So although our function is undefined at x equals 3, when we get really, really close to 3 from either side, we're going to be approaching the value of 6. Let's find the limit as x approaches negative 2 of x plus 2 over the square root of x squared plus 5 minus 3. Now, taking a look at our denominator, if we plug in negative 2, underneath here we're going to have 4 plus 5, the square root of 9, minus 3. We're going to get a 0 in the denominator, and we know that's a problem. We want to simplify this or algebraically manipulate it any way we can so that we don't end up with a 0 in the denominator. What we're going to do with this type of problem when we have a radical in the denominator like that is we're going to rationalize the denominator. The hardest part about calculus is definitely the algebra within it, that we have to be prepared to pull out any algebra technique we've ever learned in the middle of one of these calculus problems. Let's multiply top and bottom by the square root of x squared plus 5 plus 3. In order to simplify this fraction, we're going to have to cancel common factors. So when I get to multiplying the numerator together, I would not distribute that. Distributing is the opposite of being factored, so if we're going to try to cancel a common factor, in the end, that's going to be counterproductive for us. In the denominator there, we have conjugates, so we can shortcut the multiplication and multiply just the first two and the last two together. Multiplying the first two together, we'll get x squared plus 5, and then a negative 3 times a positive 3, minus 9. Let's clean this up. We have the limit as x approaches negative 2. Our numerator is going to stay the same. Our denominator is going to become x squared minus 4. We still have a problem if we try to substitute negative 2 in for x. I'm still going to get 0, so I know I can't be done with my simplification. I notice that I have the difference of 2 squares in the denominator. And yes, you got to write your limit notation. Every time you're rewriting, we need the limit as x approaches negative 2. Now that we've factored the denominator, we can see that x plus 2's are going to cancel out. That leaves us with the limit as x approaches negative 2 of the square root of x squared plus 5 plus 3 over x minus 2. And now if we take this negative 2 and plug it in for x in our denominator, we get negative 4 and not 0. So we should be safe to plug it in everywhere. Now that we're actually plugging in negative 2 for x, this is when we drop our limit notation. Square root of negative 2 squared plus 5 plus 3 over negative 2 minus 2. In our square root there, we're going to have 4 plus 5. We get square root of 9 plus 3 over negative 4. 6 over negative 4, which will simplify down to negative 3/2. So if you have a radical in the denominator and when you plug in it's undefined, you want to rationalize that denominator. Let's take a look at a piecewise function. You'll notice in our parts A, B, and C, they're asking us to find the limit as x approaches 2, maybe one-sided, maybe not. And you'll notice that our piecewise function is broke up at 2. Now, if they had asked us just to find the limit as x approached 0 of f of x, we wouldn't have 3 parts A, B, and C. See, if we were finding the limit as x approaches 0, well, this top function is when x is 0, so all we would do is take 0 and plug it in for x and simplify. But since the limit we're being asked about is where they break it up, we have to first look at the left and right hand limits first, and then figure out what the limit as x approaches 2 is. If those left and right side limits match, then the limit exists, and it exists at that matching number. And if they don't match, then the limit as x approaches 2 is not going to exist. All right, so the limit as x approaches 2 from the left, so we're looking at numbers that are less than 2, therefore we're going to be using this top function. That's the limit as x approaches 2 from the left of x squared plus 6, but we're still just going to plug in our a value, 2, as long as it's in the domain. And since we have a polynomial here, we know that it's in the domain. It's going to become 2 squared plus 6. Our limit's 10. In part B, we want to look at the limit as x approaches 2 from the right. Now, the right side of 2 means that we're looking at values that are a little bit larger than 2. So we'll be using the x to the third plus 2. The limit as x approaches 2 from the right, x to the third plus 2. We have a polynomial here, so we're just going to plug in our 2. 2 to the third plus 2, 8 plus 2 is 10. And we'll notice that our left and right hand limits match. So that brings us down to our part C. This limit as x approaches 2 of f of x will be equal to 10, because the limit as x approached 2 from the left of f of x was equal to the limit as x approaches 2 from the right of f of x. If they didn't match, we would say that this limit does not exist.